Thanks a lot for the invitation and welcome to our talk. My name is Cedric. I'm a final year PhD student with Hoeffding, and together with Merve, we're going to present to you data-centric challenges in the operational stage of ML ops. So when we look at the machine learning lifecycle, we can identify two different sub-cycles. And you have seen this in the previous talk already, but let me quickly recap. So on the one hand, we have the development cycle, where you typically use data to train a machine learning model. And then if you're not happy with the model, well, you either try different approaches to train, or you go back to your data, fix it, change it, and retrain a new model. On the other hand, we have the operational cycle, where when you have a bunch of trained models and the production data comes in from a stream, you use that data to test or adapt the models and pick the one you should use at a given time. Now this repeats over and over again. So both cycles have data-centric challenges, but in different ways. And in our group, we've been working on unfolding these two cycles in a bunch of different projects, which you saw yesterday. But for today's talk, we're going to focus on the right side of this picture, and we're going to focus on two projects we've been looking at. So what are the data-specific issues or challenges we have in the operational stage? In the operational stage, you usually have data which comes in form of a stream. The data may consist of some features and is usually not labeled. Okay? Now you use that data, or you change that data by labeling it, and you use it in order to test your machine learning model or models by measuring some metric, which is usually accuracy, fairness, or robustness. Now, the challenge we see is how can you use the data as efficiently as possible while remaining statistically sound? And the two sub-questions we have been identifying is, on the one hand, how often can I reuse my samples? And which samples do I need to label in order to make decisions in production? I'm going to focus on the first question in my talk, and Merve is going to dive into the second question. So the first question we want to answer is, how can I use my test data whilst remaining statistically sound, and how often can I reuse it? In order to tackle this problem, we have been building a system which we called Ease.ML CI, which is a continuous integration engine for machine learning models. And of course, this was not an effort by one single person, but I had help from many collaborators you see on this slide. Now, the motivation from building Ease.ML CI comes from the fact that if you're not very careful in using machine learning, you have nothing else than a very powerful overfitting machine. And let me explain to you why this is. So if you, for instance, have a scientist which is not very familiar with using machine learning, but still wants to use the newest techniques on her data, she would typically use the full data set to train a machine learning model. Now, everyone knowing a little bit about machine learning knows this is not super wise because, well, it will not generalize to the production data. So what's the remedy to that problem? Well, you typically split your data into two sets, and you use one set to validate and get an accuracy estimate, and you train on the other one. Now, if you do that and you choose some hyperparameters using the validation set, you're still left with the same problem. You're still overfitting to the validation set, and the accuracy you're getting in production will be far off. So standard machine learning textbooks suggest to split it in three subsets: test, validation, train. You use validation to choose some hyperparameters and only evaluate it on test once you're done to get a proxy of the accuracy you can expect in production. Now, are you safe now? So what guarantees you that you don't overfit to the test set? And in fact, you're not. So we have seen scenarios where when you look at the evolution of trained test and the true test, which is the accuracy in production, this might be very different. So an iteration here is committing a new model and iterating on the model. So obviously, training set accuracy going down isn't too bad because it's not really the quantity that matters, but it might even indicate in that case that you start generalizing better. But the gap between the estimated test accuracy and the true test accuracy is really what we quantify as overfitting to the test set. And this gap typically, or could, become larger over time because you get better test accuracy because that's the quantity you care about, but it doesn't generalize to the underlying true distribution. So what we want to achieve is to provide some statistical way to control the overfitting tolerance. And that's the system we have been building, which is Ease.ML CI. So as an overview of how our system works, we have developers doing some error analysis and iterating on the development set. On the other hand, we have a repository here, GitHub, where developers will commit a new model. Now, inside this repository, we will use the test set, which is hidden from developers, to evaluate some conditions, and I will go into more details afterwards, some conditions this new model needs to satisfy, and we will return either a failing signal, the conditions are met, or a passing signal. If the conditions are met and we return a passing signal, we will replace the current model in production with the new committed one. So what is hard about this? Well, we want to have some statistical rigorous guarantees, but remain as cheap as possible, meaning that the test set, obviously, if it's infinitely large, that's an easy problem, but we have finite samples and we want to reduce the number of samples we require in this test set as much as possible. Secondly, even if you return a binary signal, failing or passing, you still leak some information about the test set. And this is what is known as adaptive analytics. Now, our results are statistically sound estimators, which enable us still to reduce the label complexity of the test set by 1 or 2 orders of magnitude. Let me go a little bit more into details about Ease.ML CI. In Ease.ML CI, we have 2 actors. On the one hand, we have managers, and on the other hand, we have developers. They have both access to a shared repository where training and validation data is publicly accessible. Now, the test set is provided by managers in a protected, encrypted way. Then managers specify the requirements a new machine learning model needs to meet in some configuration file. Such a requirement could be that every new model just needs to meet a certain threshold of accuracy, being above 80%. But bear in mind that machine learning is inherently statistical, so we need to provide some epsilon delta approximation. Now, developers will then commit a stream of T models, and after every commit, they will receive a pass or failing signal. After those T commits, the system will automatically ask manager to provide n new test samples with their labels, potentially, and downgrade the existing test sets to be part of the training and validation set. Now, as I said, the managers need to specify the requirements. And in Ease.ML CI, we have the possibility to provide a rich set of different requirements. So one typical requirement is to require a new model to be better than the old model. Otherwise, you don't want to replace it by, let's say here, 1% with high probability. Now, we can also, in order to prevent failures in production, we can bound the number of difference in predictions we want to allow between the new and the old model. We can also have the condition from before, which is a very simple one, which we don't care about the active model in production. We just require the new one to be better than 0.8. And finally, we do also allow for arbitrary combination of requirements and making more complex ones like this one we show here on the bottom. Developer's task is very easy. After having worked on a model, she would typically commit this new model to the repository. After the system evaluates the condition, it will return, for instance, a failing signal. Based on that signal or on that insight, developers know that they need to rework on the model and provide a new one, a better one, by either iterating on the data or on the model, and then submit this new model. And hopefully, it will at some point return a passing signal and replace the model in production with the committed one. So the core technical challenge of Ease.ML CI lies in adaptive statistical queries. And tackling these is inspired by some related work, but most notably the one by Bloom and Hart in the latter paper. So what is adaptive analytics? In adaptive analytics, you typically have NIID samples from some unknown distribution, and developers do not have access to those samples. Now, developers will provide a function, an initial function f1, which here is a function which enables the evaluation of the new model. And the system will run a function g on this function f1, which in our case is evaluating the test requirements and return the binary signal to developers. This gets then repeated for capital T steps. Now, the contract between the user and the system is given by this epsilon delta approximation, which simply says that the probability of a result lying outside a certain confidence interval specified by epsilon should be smaller than delta. Okay. Now, given an epsilon and a delta and a capital T, the question we want to answer is how many samples do we need in order to meet that contract? And can we decrease the dependency on M as much as possible? So if you have a single step, that's not a too hard problem because Statistics 101 offers us the toolbox to solve that problem. And especially concentration inequalities like Hoeffding, which we use here, are a very nice way to bound the empirical mean from the true mean. And we can use that formula and rewrite it such that we have a lower bound on the number of samples which we need in order to meet the epsilon delta requirement. Now, for multiple steps, it's a little bit more involved, and we have different approaches. So what we call our baseline approach is to simply resample. So we want to require new samples for each step. Now, for typical values of epsilon delta and capital T, here we set epsilon to be 1%, the size of the confidence interval. Delta, the probability of lying outside, should be 0.1%. And we have 32 commits, which we want to support. And why 32? If you think about one new model commit every day, that's basically 1 month worth of commits. Then our baseline approach for a very simple requirement would require us 1.7 million samples each month. That means 53,000 samples every day. Now, this is clearly too expensive. So another approach, which is given by the latter paper, would enable us to reduce that number by a lot, but it's not really applicable in our scenario because the latter paper has some constraints on how G should evolve over time. And in our case, G is non-monotonic, so we cannot apply the same techniques. For the sake of completeness, there are also differentially privacy-inspired approaches, which are not straightforward to apply, and we don't really know how we can add some meaningful noise to our function in our system. So how do we approach this problem? Well, we follow a very systematic approach, which is to optimize the sample complexity for specific regimes that our system cares about. And more specifically, in our paper, we have 4 different optimizations. And in this talk, I'm just going to focus on 3 of them. So the first observation we made is that actually the most trivial approach to reduce the sample complexity is not that bad. And what do I mean by that? Well, in our case, as I mentioned before, we know that our function g returns a binary signal. Now, for capital T steps, there are only 2 to the power of t, which could be large, but in our case, you'll see why this is not the case. There are only 2 to the power of t number of possible functions that over t steps that it can return. And one approach is to simply apply union bound over all those possibilities. So if we apply union bound and reshuffle this, we get a lower bound, which still is linear in t, but because t is not too large in our case, we can, from a baseline from 1.7 million samples, we can reduce this by 1 order of magnitude. All right. The second observation is for very specific types of requirements, And one of the most popular we see in Ease.ML CI is given in this form. So we want the new model to be better than the old model by at least 1 point, but the difference in prediction should be less than 10%, right? So now we have two key observations when we look at this. First of all, estimating the difference in prediction doesn't need labels at all. So we need samples, sure, but we don't need any labels. So we don't care whether it's the prediction was correct or not. We just care that they are the same. And the second observation, if we condition the first part of this requirement on based on the second one, so we know that this will have small variance. And we can make use of this fact by taking another concentration inequality, which is Bennett's, and by having finite variance and especially having small finite variance, we can reduce the number of samples by a lot. So again, we have this our settings for epsilon, delta, and t. Now our baseline here requires much more samples than before because the condition is more complex. So we have two parts of the condition. If we apply union bounds, well, we can reduce the number of samples required by 1 order of magnitude. And additionally, applying Bennett's inequality, this gives us another order of magnitude saving compared to the baseline. Finally, the last observation, which I already mentioned, is that not all labels are useful. And this is not only the case for estimating the difference in prediction, but this is also the case for estimating formulas like this. So let's assume you want to make sure that the new model is better than the old one by 1%. Now let's assume we have 5 test samples, and the old model predicts 0, 1, 1, 1, 0, and the new model predicts 0, 1, 1, 1, 0, 1, 0, 1, 1, 0, 1. So now, in order to estimate this quantity n minus O, we don't really care whether the first 3 samples were correctly labeled or not, but we only care about the last 2. So in other words, if a new model and an old model are only different in predictions with a small probability, we can save in terms of labels, not samples here. We care about labels because these are typically much more expensive to acquire compared to samples without their labels. And more formally, so if the probability of the 2 models being different is of some order square root of epsilon, we have the number of labels we require is of order 1 over epsilon compared to 1 over epsilon squared, which we had in standard Hoeffding before. So the savings for small epsilon could be quite significant. Just to give you some rough numbers, for this condition using Hoeffdings, we would need 50,000 samples per signal, and having a difference in probability being in the order of 10%, we would require 2,200 labels per signal. So here we assume that the samples without labels are free. All right, so let me conclude this part of the talk by giving you some rough numbers to see what are the savings in terms of samples we can achieve using Ease.ML CI. So we again look at the case where we want to support 32 commits, and we differentiate between 2 use cases. One being the popular use case where epsilon is relatively small, around 0.01, and one cheat mode where we just double the size of the confidence interval. Now we compare the baseline approach, which is resampling, against applying all the optimizations we can in Ease.ML CI. So for the more complex requirement, we can achieve 2 orders of magnitude savings compared to the baseline. Now for a simpler condition, the savings are only 1 order of magnitude because we cannot apply all the optimizations for the very simple requirement. If we evaluate it on the same requirements in the cheat mode, we see that this trend of 2 orders of magnitude for the more complex requirement and 1 order of magnitude for the easier one still holds. Now, just to give you some intuition about how much 300 labels a day or around 330 labels a day are, if we think of a labeler or a person requiring 10 seconds to provide 1 label, then 300 labels a day are really less than 1 hour of work by a single person per day. And the question is really, is that too much in order to make sure that you have very strong, rigorous guarantees? So if you want to know more, please feel free to visit this website. There is much more description, the papers are related there, and there's also access to the code. So feel free to play around or send me an email if you have any question. With this, I conclude my part of the talk, and I will hand over now to Merve. Thank you.
Hi, everybody. I'm Merve. I'm a PhD student here at ETH and supervised by Professor Zang. Today, I'm going to talk about how to perform active model selection with limited labeled data. So this work is a product of our great collaborators here at ETH Zurich. So in the first part, Cedric talked about how we can continuously test the quality of the ML models without overfitting. So in this talk, I'll focus on the next step, which is how to acquire production data to tackle with domain drift problem. So the machine learning practitioners have trouble sleeping, asking, will my model trained yesterday be working well tomorrow? So to understand the severity of this problem, let's take a look at a time series data. So a single model that is trained previously will not work well in these time intervals because of data drift. You may ask, okay, isn't this a domain adaptation problem? Yes, it is, but there are thousands of methods available that can be applied to this. So, and probably there is no single domain adaptation approach that can cover all the possible circumstances. And those are including the new and different domain adaptation approaches, new ML models, and the same models with different assumptions and hyperparameters and architectures. So in this work, we propose modelpicker, which will take the pool of candidate pre-trained models that you can use for your freshly collected data, and take these as input and do labeling with limited budget and output you the best model to use for the rest of the day or rest of the hour to make prediction on your target task. Then the question that modelpicker asked, but how can we minimize the amount of labels we acquire from human so that we can output the best model? So in this work, we answered that question and we show that this can be done in an extremely label efficient way. So for instance, just to pick one best model on ImageNet dataset, we only need to query the labels of 12% of the entire test set. So in the end, the model picker is a cheap and effective process that you might want to run on your ML products every hour. So I briefly talked about what is a model picker, and then I'll talk about why do we need a new sampling method, what is the issues with the current ones. And then I will talk about two different algorithms, differently for two different settings. And then I will introduce the evaluation pipeline for model selection in general. And then I'll show results on many different data sets and illustrate the benefit of model picker. So why do we need a sampling method? Imagine you have millions of data sets and each of them has certain information. But I would like to set my information measure such that I query the most informative ones to output the best model in the end. So then the question is, how do I measure this information that is specifically for model selection? So this selective sampling strategies have been discussed a lot by active learning strategies. But the problem with that is they focused on estimating a generalization error, which is not really ranking of the models. So it is, if you want to do model ranking, estimating generalization error will give you a very slow convergence. And secondly, it heavily relies on the disagreement because it wants to label the instances that tells you about the decision boundaries rather than the model ranking. So there are some active learning approaches that focuses on model selection, but often they involve training. But we don't do any training here, and this will slow down the model selection process. And lastly, most of them have very strong underlying assumptions on the models where we are completely agnostic to the machine learning model and the architecture. So let me first talk about our proposal in the online setting, which is simply that the data instances come one by one instead of having them available altogether to us. So let's say we have at the time instance 0, we have one unlabeled instance, and we have 3 models for the scenario that makes binary predictions, and we have the model predictions. So then the question is, should I ask my label expert to label this data point? So at the very first instance, we just flip a coin, and if it comes heads, we will ask the expert, and if it comes tail, we will throw away the instance. Of course, you don't have to throw away the instance physically, but that means we won't use that instance anymore. And then I get my answer, yes, for this instance, and then I will ask the expert to label it, then I'll move on. So I have the second instance now, and I will ask the same question. So, but there is one thing that I would like to get your attention to, which is that now I have some evidence, which is the partial labeled instances. So I would like to use this, and I would like to calculate a posterior belief on the models based on this evidence, which is the labeled data. But in addition to that, the new instance here also has some uncertainty, the second instance. So I'm also going to incorporate its uncertainty in the form of hypothetical loss into my system. And using these 2 information, I will flip a coin, then I will decide whether to ask it to expert or not. So repeating the same thing for the third instance. So here I will again calculate the posterior belief based on the partial label data, but just heads up. So here I didn't query the second instance, which means that I still have the same evidence as before. So my posterior belief will not change compared to the previous instance. And I will again use the hypothetical loss for this instance. Then I'm going to flip a coin based on the bias I formed from these information. And then I move on. And then once I go through all the streaming instances, then I'm going to return the best model based on this labeled instances. You can either try just choose the one with maximum accuracy on this labeled instance, or you can look at your posterior belief and output the model that has the higher probability. So just to briefly go over what we actually did in this posterior update and hypothetical loss state is that we update the posterior with exponential weights, where LT is the accumulated loss based on previously labeled data, and nu T here is a decaying tuning parameter. So we update the posterior. Well, at this hypothetical loss state, we just check the hypothetical loss for each possible instance. So if the true label is 1, what will be my hypothetical posterior update, and if 0, what will be my hypothetical posterior update. And using these, I'm going to form a bias, which is simply the variance of this hypothetical loss over the posterior distribution, which you can also compute via this expression. So this will be my coin flipping bias, and using this bias, I will flip a coin. Basically, I will just throw a binary random variable with this success probability, and I will decide to label it or not. So we have a lot of theoretical guarantees for this methods, both in stochastic and adversarial settings. And I would like to give shout out to my joint co-author Mohammed Reza Karimi here. So for failure probability, we show that it exponentially decays over the stream, where the capital T here is the stream size, where K is the number of models. So lambda here is hardness of the problem, which simply relates to the gap, accuracy gap between the true best model and the second true best model. And In addition to this guarantee, we also have accuracy gap guarantee, and we show that this is very small at every round, where epsilon is the accuracy gap here. Of course, the accuracy gap also depends on lambda, which is the hardness of the problem. And finally, we show that number of queries is gracefully increasing with capital T, which is very consistent with all the regret minimization approaches. So yes, so we have theoretical guarantees, we have an algorithm that is designed for model selection, but does it actually work? So before moving on to experiments, I would like to give you some preliminary. So first, how we set the data set, or how we form this data set and model collections for this task. So we first have a train validation and test set, and I would like to evaluate all the methods on the same streaming instances. So I keep my test set, but I split my training and validation sets. So these splits don't have to be completely different, disjoint. They can have huge overlap. They don't have to have overlap. So we combine all these cases, and we form many different model sets on different data sets. So you can see here it varies in the number of clusters and number of instances and models, and also we do this for many for models that covers a huge range of accuracies. And for the baselines, we set there is no baseline, but there are other strategies to select the most informative instance. So among them, we adapted the most suitable ones for model selection tasks. So for instance, the query by committee, which basically looks at the uncertainty that instance create over the models, and it normalizes it to make a coin flipping probability. And we also have a structured version of query by committee. And this forms a posterior belief among the models, and then look at the two competing methods instead of all models. And another approach is importance-weighted approach, where it selected instances which minimizes a weighted loss. And finally, there is label efficient prediction, which is a regret minimization approach, and that is simply the fixed sampling bias in this case. And how did we evaluate it? So I want to go through the setting briefly. So we have model selectors, many model selector approaches, baselines and model picker, and we have a streaming instance. And at every instance, we just flip a coin. And this goes on, and at the end of the stream, all these model selectors output the winner dating it is. So then the question is, how do we compare these model selectors? Because they will query different amount of labels. So if one query is 100 labels, if the other 1,000, how will I compare them fairly? So to achieve that, we fix the cost and compare the performances. So instead of cutting the stream off once they query a certain amount of labels, we just introduce a hyperparameter that scales the bias for each model selector separately, such that at the end of that stream, they all query the same amount of instances because they all have seen the entire set of instances. So we will do it for various budgets and compare the performances for different cases of costs. So once we did that, we have the first evaluation measure, which is a success probability. So over many realizations, we will check the fraction of times that these model selectors actually return the true label, true winner. And as a second measure, we will check the accuracy gap. So not always we will, or any of these model selectors will return the best model, but once they don't do that, do they still return a good model? So to achieve that, we measure the expected gap between the accuracies of three winners and the returned winner over all these realizations. So let's take a look at the success probability first. Of course, in this case, I want the success to be as high as possible. So for a SciPar 10 data set, So we see that there's significant improvements brought by model picker. So if you look at the percentages, these improvements are about 5 to 10%. So here I just would like to get your attention to this query by committee, which is the competing method. So this is not the plain method, so we adapted all these baselines for this task. But it's still quite, it performs quite competitively. And in the second data set, ImageNet, we see the effect of model picker even more because there are a lot of classes here, and all these other baselines are not really powerful in measuring the information in such a case. So both these data sets, we have models in a huge range. So then we did another experiment on a very interesting data set, where it has a lot of domain drift. Basically, each model is trained on a very different training distribution. And it is very hard to find the winner model in such a case because of the drift, especially in the streaming case. So for this case, you see that, for instance, the competing method query by committee completely fails because it's not able to identify the most informative instances due to noise. As another interesting case, we also did experiments on a data set where there are only good models. So in this case, you see it's the hardness of the problem is very low, and you see that the model picker is still able to bring improvements. So this is also a crucial case, as if your application is safety critical, you might want to have as high accuracy as possible, and even the small improvement might be very important to you. So now we analyze if they are actually able to output to true winner. And just one remark is that, for instance, in this data set, it takes only 12% of instances for model picker to find the best model with high confidence, where the stream size here is 10,000. So now let's take a look at the accuracy gap. So in this case, we want the accuracy gap to be small because we want the model we return to be as close as the best model. So we measure the accuracy gap over all these data sets, and you see that model picker is actually really good in ranking the models, especially the competing models as well, and the accuracy gap shortly reduced to very, very insignificant amount after small amount of labels. So far, I talked about how we can select the best model from a candidate of models. So this approach is flexible in the sense that you can use the stream-based scenario, which is very powerful in detecting domain drift and adversaries in pool case as well. So you will have that flexibility. You will just throw away one instance at a time and treat this as your streaming instance. And also because of the guarantees of stream-based setting on the adversarial data, I show you that this approach is also very robust, as the theoretical guarantees also holds for the adversarial case. And you can try out model picker here using your own data. You just need to do the labeling, and model picker will take care of the rest. So just to wrap up, Cedric and I introduced you today the continuous quality optimization, continuous integration, and tomorrow Luca will talk about automatic feasibility study without overfitting for ML systems. And thank you for listening.